Hey there, welcome back to Calculus. We're going to wrap up section 7.3 on trigonometric substitution, just showing a couple of examples of how to treat definite integrals. So the method of trigonometric substitution itself is kind of out there, and we have all the techniques we need to practice these things, but we didn't do any with definite integrals, so I want to just do some with definite integrals today. So that's what our topic list will be. I've got some examples that we'll treat with trigonometric substitution that require definite integrals. My first example will be a volume problem to kind of circle back through and remind you of some of our applications. And then we'll end with just a quick discussion for those of you who have looked at hyperbolic functions. That's in the end of chapter 3 in our text. You can also use hyperbolic trigonometric functions to make some of these substitutions. And in a lot of cases, the algebra is a little bit easier because the differential calculus of hyperbolic functions is a little simpler than regular trigonometric functions. Okay, so that's what's on the program. Let's just get going here. So first example, I can't really, that's just going to barely fit on the screen there. So I'd like to find the volume of the solid formed by rotating the graph of x times the square root of 1 minus x squared. I've got that function graphed there for you already. It's written in blue, drawn in blue rather. Let me just write the equation of that thing is x times the square root of 1 minus x squared. I'd like to revolve the region bounded under that graph on the x-axis. It's given that it's over the interval from 0 to 1, and I want to revolve it around the axis x equals 1. I've drawn it in the picture there. It's a vertical line, equation x equals 1. So if I were you, I'd kind of stop the video here and try to proceed to set up the integral yourself. Some of the questions I'd kind of want you to be able to answer is, are you going to do this with disks or shells, and why? And then once you have that decided, can you write down the appropriate information to get the integral going? So pause it and think about that. I'm just going to keep going to keep the video short. I'm going to use shells. I'm going to use shells because I was given a function of x, so I don't really want to solve that for x in terms of y unless I have to. And I'm rotating it around an axis that's parallel to the y-axis. So that's kind of out of the box. I want to try to use shells. Okay, so let me draw my usual. Let me pick an x value somewhere between 0 and 1. I'll draw it on the axis down there. This is x equals 1 at the purple line. Just sort of draw my usual shell segment there. Okay, so I can see the height of my shell segment is just going to be my function value. So I can write down the integral that I have to compute right now. How do we do it? Well, the volume of this thing using shells, I'm going to put my 2 pi out front. It's going to be an integral from 0 to 1. Those are the extreme values of x. And then I need to take my shell radius. What's my shell radius? Well, it's the distance from the shell segment to the axis of rotation. That's because the axis of rotation has a bigger x value. My shell radius is 1 minus x. 1 minus x. What's the height? It's x times the square root of 1 minus x squared. It's the equation that bounds the region there, and I need to integrate that dx. All right, so there my integral is set up. And now I'm just going to do a little bit of algebra on this thing to see what kind of integration techniques. Let me put my 2 pi. Let me just distribute that integrand out in there. So distributing through the 1 minus x, I mean. So I've got x times that square root factor times 1. Okay. Oops. Premature differential there. And then we're going to subtract x times that square root factor. So that's x squared. Okay. Now I'm going to scroll a little bit so I have some more room to work. These expressions, I have to multiply 2 pi by that integral. The way I'm going to treat this integral will depend on what part of it. The x times the square root of 1 minus x squared, I'm going to do a u substitution on that. Yeah, because the derivative of 1 minus x squared up to a constant is x dx. So that one's going to be an elementary u substitution. This integral, x squared times 1 minus x squared, is going to require the trig sub. Okay, so I'm going to split those two integrals into two. I'm going to leave the 2 pi out in front. See if I can squeeze all of this in here. So 2 pi, I'm going to separate the integrals 0 to 1 of x times the square root of 1 minus x squared. Why am I separating them? Because I'm going to integrate them with different techniques. Then I'll subtract the integral from 0 to 1 of x squared times that square root factor. All of that has to get multiplied by 2 pi. All right, so you can organize work the way you want to. When I'm doing an integral like this, instead of keeping it line by line, I'm going to use a different technique here than I am here. I kind of like to organize it with side work. All right, so I'm going to just kind of give a temporary name here to this first integral, like I1, and then a temporary name to the second integral, I2. You don't have to organize your work this way, but I'm going to now just kind of go compute I1 and I2. When I get done all computing them carefully, I'll come back and subtract the second one from the first one. And when I've got that difference, I'll multiply the whole thing by 2 pi, and then I'll have my final answer. Okay, so that's how I'm going to choose to organize my work here. So I'm going to leave visible what I need to compute I1. The 2 pi I'm dropping out. I'll multiply that by at the end. Okay, so I'm just what I've underlined there. I1, let me write it again. I want to compute the integral from 0 to 1 of x times, I'm going to write this square root as the 1/2 power because pretty soon here I'm going to go to integrate it. So I'm going to make a substitution. I'm going to let u equal 1 minus x squared. So du is negative 2x dx. And then I'm going to start substituting. Okay, 1 minus x squared gets replaced with u. X dx gets replaced with minus 1/2 du, and I'm going to put the minus 1/2 out front. And then I'm going to use my substitution to change my limits. When x is equal to 0, u is equal to 1 minus 0 or 1. And when x is equal to 1, u is equal to 1 minus 1 or 0. So the limits end up switching. All right, so maybe to keep them and get rid of that minus sign, I'll use a property of integrals, change the limits back to 0 to 1, getting rid of the minus. Trying to minimize my errors here. Now it's antiderivative time. The antiderivative of the 1/2 power is 2/3 of the 3/2 power. Integrating that from 0 to 1. 1/2 times 2/3 is 1/3. Plugging in 1 into the square, the 3/2 power is 1. Plugging in 0 gives 0. So we've calculated our value of I1. Our value of I1 is 1/3. Okay, got it written down. So now I can go focus on what I2 is. Got to compute I2. That's where the trig sub is going to come into play here. So let me write it again. You can't see it anymore, but I'll remind you that I2 was the integral from 0 to 1 of x squared times the square root of 1 minus x squared. Okay, hopefully you've studied this stuff, that you're motivated to know that the trigonometric substitution I should use is x is equal to 1 times the sine of theta. Okay, so dx is equal to the cosine of theta d theta. And our square root term, square root of 1 minus x squared, is going to simplify to cosine theta after the trigonometric identities are done. All right, so let me start substituting here. So I've got an integral. I'm not going to write limits here yet. I've got an integral. The x squared term gets replaced with sine squared. Square root gets replaced with cosine. Dx is cosine. Okay, but what about those limits of integration? What about those limits of integration? It's just like with u substitutions. The equation that transforms the variables is where I go, but this is going to be a little different. Remember, I'm starting with x values and I want theta values. This is not giving me that right out of the gate, right? This does not have theta solved for x. This has x solved for theta, right? So we need to plug in x values here. So let's start doing it down below here. When x is 1, what does our equation say? 1, well, sorry, I should start with x equals 0, the lower limit. So the equation says 0 is equal to the sine of theta. Okay, well, because theta is in between minus pi over 2 and pi over 2, I can use the inverse trig function. So if the sine of theta is 0, then theta is 0, right? But if I let x equal 1, my equation becomes 1 is the sine of theta. So again, using the inverse trig function inverse sine, the inverse sine of 1 is pi over 2. The angle between minus pi over 2 and pi over 2, whose sine is 1, is pi over 2. So that's my new upper limit of integration. Okay, so pause and think about that. It's a little bit different. Now let's start integrating. So what do we got? We have the integral from 0 to pi over 2 of sine squared theta times cosine squared theta. So that's a section 7.2 integral where both of our exponents are even. Remember, that's an unhappy case. So there's a video where I showed you how to do this integral actually by using reduction formulas. And in that video, I said there are other ways to do it. Let me illustrate that another way right now. So I'm going to use a trig identity. First thing I'm going to do is write sine squared times cosine squared as sine times cosine quantity squared. All right, and then the trig identity that I'm going to use, let me write it over here, is the following, that the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. That's a double angle formula for sine. In particular, 1/2 the sine of 2 theta is sine theta cos theta. So I'm going to come back over here to my integral now and replace sine theta cos theta with 1/2 sine of 2 theta. Of course, I have to square that. All right, so proceeding. The 1/2 squared is a quarter. It's a constant. It can come out front. Integral from 0 to pi over 2 of sine squared of 2 theta. So how do we integrate sine squared? Well, we do it with the formula, the identity, right? The sine squared of an angle, we've talked about this before, it's 1/2 1 minus the quantity of cosine of 2 times that angle. So I'm going to put that in here. The 1/2 is a constant. I'll bring it out front. And I'm going to replace that sine squared of 2 theta with 1 minus the cosine of 2 times 2 theta. That's 4 theta. Nice. Okay, so I've got 1/2 times 1/4 is an eighth. Now I'm integrating. Antiderivative of 1 is theta. The antiderivative of cosine 4 theta is 1/4 the sine of 4 theta. Okay, and I'm going to integrate that from 0 to pi over 2. Great. So 1/8, plug in pi over 2 for theta, subtract. When you multiply pi over 2 by 4 theta, you get 2 pi. The sine of 2 pi is 0. Good. Minus plugging in 0, again, would be 0 in both terms. So you get pi over 2 times an eighth, or you get pi over 16. Okay, what is that pi over 16? That's the value of I3. Cool. So all we have to do to finish this problem is to pack it back up. Remember our original integral. I'm not going to scroll. I'm just going to remind you from above. It was 2 pi times that I1 minus that I2. Excuse me. There is no I3 here. Okay, so what do we got here? Let me do the arithmetic with you. So it's 2 pi. We calculated above that I1 was 1/3. Subtracting off our value that we just calculated for I2 is pi over 16. You can leave it like that if you want to. You could get a common denominator. I'm just going to write this and give you kind of a challenge to see if you can reason it out to be the same thing. The prettiest way I could find to write that would be something like pi over 24 times the quantity 16 minus 3 pi. So see if you can verify that. Okay, so there is an example. Well, reminding you of volumes, we did some shells. It also kind of had a nice feature that we had to, maybe while I'm talking, I'll go back and kind of look at some of this stuff. So we had to remind ourselves about how shells worked. The integral involved two different techniques, and so I split it into two integrals, and I worked out the two separately. One with an elementary substitution, it went pretty quickly. The second required a trig sub, and this was the new part, that we had to change our limits of integration on the trig sub, and instead of plugging directly in and finding the new value, because the trig sub formula kind of gives you the variables in the other order, we had to plug in for x, pardon me, I just circled the wrong thing, and then solve for theta. Okay, so we had to plug in for x and then solve for theta. Nice. Okay, stop the video, digest the details. I'm just going to do another one. This one, no context, it's just trig sub, but I wanted to pick one and do it together with you guys that it doesn't make it as clear what the a is, right? In trig sub, we're sort of looking for this expression like a squared minus x squared. So here, the coefficient in front of x isn't a 1, and that's kind of ruining things. So you don't have to be afraid, though. We'll just factor it out and make the coefficient a 1. So what am I going to do? Before I do any calculus, I'm going to just, underneath that square root, I'm going to factor 9 out of 4 minus 9x squared. You factor 9 out of 4, well, you get 4/9. Okay, I can take the square root of those two things separately, and the square root of 9 is 3. 3 is a constant, so I'm going to just throw it out front. So now it's in a form that I can kind of see what my a is. Yeah, the a must be 2/3. It's the number whose square is 4/9. Okay, so I'm going to do this over here. I'm going to let x equal 2/3 sine of theta. So dx is 2/3 cosine of theta d theta. Okay, and the square root of 4/9 minus x squared is going to become 2/3 cosine theta. Cool. So I've got a 3 out front. Hold on for those limits of integration. We just said the square root of 4/9 minus x squared becomes 2/3 cosine theta. Dx is the same. So there's the algebra of the integral transformation, but we need to do our limits, yeah? So I have to take the equation that relates x and theta, but remember, I'm plugging in x values, right? Those limits of integration on an x integral are x values. So if x is 0, the equation becomes 0 is 2/3 the sine of theta. Well, that means theta is 0. So the new lower limit is also 0. If x is 2/3, our equation becomes 2/3 is 2/3 the sine of theta. Cancel that 2/3, and it says the sine of theta is 1. So that means theta is pi over 2 again. Maybe it's a bad example because it's not always going to be pi over 2, but you use that inverse trig function to find it. And now I don't ever have to switch back. Just for a definite integral, I'm never going to draw that little triangle and switch back to the x variable because I've changed my limits of integration. All right, now I better concentrate on the constants here. I've got 2/3 times 2/3, that's 4/9. Can you see where I'm looking? 2/3 times 2/3 is 4/9, times 3 is 4/3. So I've got 4/3 out front, and it's the integral from 0 to pi over 2 of cosine squared theta d theta. How do we integrate cosine squared? That half angle formula. So we're going to write 4/3 times 1/2 of the integral from 0 to pi over 2 of 1. Cosine squared is 1 plus the cosine of 2 theta. Good, getting these identities down. 4/3 times 1/2 is 2/3. Antiderivative time, theta plus 1/2 sine 2 theta. Evaluating that from 0 to pi over 2. So we've got 2/3, plug in pi over 2, plus 1/2. The sine of pi is 0. Lower limits will both give 0. So we end up with 2/3 times pi over 2, and that is pi over 3. So there's a second integral where trig sub required changing the limits. If you didn't like it, if you don't like this changing the limits of integration part, I think you should. But if you don't, if it makes you uncomfortable, then you can do this as a indefinite integral everywhere. But then after you integrate, as soon as you get to this stage, then you're going to have to use that little triangle to get back to x, so you can use the original x values as your limits of integration. I personally think if you change variables on a definite integral, you should change the limits and just keep going. But you don't have to agree with me about that. Okay, so those are the primary examples I wanted to do. I wanted to just mention something for those of you who had a good Calc 1 course and you studied the hyperbolic trigonometric functions in section 311, the hyperbolic cosine, the hyperbolic sine, and so on. I'm not going to review that material here. If you need to review it, to go look at it. If you've never seen it, it's certainly worth a read. It can expand your horizons. The hyperbolic sine and cosine, which notation is written there, cosh and sinh is how they're pronounced. They don't satisfy an identity cosh squared plus sinh squared is 1, but rather cosh squared minus sinh squared is 1. Okay, so that's the kind of fundamental trigonometric, hyperbolic trigonometric identity. So if you gave me an expression like x squared minus a squared, I mean, we know we could let x equal a secant theta and proceed. But instead, if I let x equal a times the hyperbolic cosine, say of y, well, then I can replace it and I would have a squared cosh squared minus a squared. Factor out the a squared and use the fact that this is coming from this identity. Cosh squared is 1. Cosh squared minus 1, cosh squared minus 1 is equal to sinh squared, is what that identity up there says. Sorry about the oops. Now I'm all over the place here. So I replace cosh squared minus 1 with sinh squared, right? Take the square root. I'm assuming the values of y satisfy that sinh of y is greater than 0, so I drop the absolute value signs, and so that square root would become just sinh. So let me just illustrate quickly, and then we'll end this video, how you could do this integral with a so-called hyperbolic trigonometric substitution. Then you can try it with a trigonometric substitution and compare the two results. So I'm going to let x equal 5 times the hyperbolic cosine of a variable called y. The derivative of hyperbolic cosine is hyperbolic sine. Okay, the square root of x squared minus 25 is going to become 5 times the hyperbolic sine. So this integral transforms into 1 over 5 times the hyperbolic sine. Dx is 5 times the hyperbolic sine dy. And here, the 5's cancel, the hyperbolic sines cancel, so we just have to integrate dy, which is certainly y plus a constant. And well, what's y? Well, we have to go back to our equation that relates x and y. In this case, I can write it as x over 5 is the hyperbolic cosine. So you take the inverse hyperbolic cosine of both sides, pardon me. End of the day, and my brain is getting tired here. In hyperbolic cosine inverse of x over 5 is y. So there is an answer, at least in terms of an inverse hyperbolic cosine. If you work out this trigonometric substitution using the 5 times the secant, your answer is going to look very different. Your answer is going to look very different, but you can relate them. I'm going to end here that there's a relationship. The hyperbolic, inverse hyperbolic cosine of a value, let me just call that value not x or y, let me call it z, just to have sort of a different flavor variable. The inverse hyperbolic cosine of z is equal to the natural log of z plus the square root of z squared, it's minus 1. Good. That's for z at least 1. There is sort of a technicality there. But when you if you work out this integral using a trigonometric substitution, letting x equal 5 times the secant, when you get all done and rewrite your answer back in terms of x, it's going to be in this form. All right. So sometimes you can have two expressions that are equal to each other, but it might not be obvious that they're equal to each other. Okay, I'm going to end the video there. Thanks for listening.